Okay, so this is section 4.6 out of Math 110. It's called linear programming. In this section, we will graph the solution set to a system of several linear inequalities and two variables, as in section 3.4. We then use the solution set to the inequalities to determine the max or min value of another variable. The method we use is called linear programming. So before we dive into a large problem, it makes sense to kind of look at the pieces of a problem. So with any linear programming, you're going to have to graph a set of inequalities. So with this example, I see four inequalities, two of which are horizontal and vertical lines. So x being equal to 0 is a vertical line through the y-axis, and then y being equal to 0 is a horizontal line through the x-axis. And so if it were just these two constraints, since x and y are both positive, we'd be limiting ourselves to the first quadrant. However, we do have two other inequalities that will be limiting the feasible region. The first one is this one right here in red. So since these are in standard form, it makes sense to me to find the vertices where they intersect the x and y axis. So when we plug 0 into x, we get y is equal to 6. And then if we plug 0 into y, we get x is equal to 4. So graphing these ordered pairs, I get 6 on the y-axis and 4 on the x-axis. And so looking at the less than sign will tell me that we're going to shade points beneath that line. So the less than will restrict us to points beneath that line. However, we still have one more inequality. That inequality is going to be graphed in blue. So to graph this inequality, I will make an xy table with the intercepts. So if x equals 0, then we get y equals 4. If y equals 0, then we get x equals 8. 0, 4 is on the y-axis, 8, 0 is on the x-axis. And then finally, having all four lines to represent the boundary lines, we're now ready to shade. And since everything is less than on the red and the blue, the feasible region, where the points satisfy all four inequalities, will look like that. It's going to be a quadrilateral in the first quadrant. So when we talk about linear programming, we have to be able to write constraints. So let's just do that for this problem. It says Jules is in the business of constructing dog houses. A small dog house requires 8 square feet of plywood, and 6 square feet of insulation. A large dog house requires 16 square feet of plywood and 3 foot of insulation. Jules has available only 48 square feet of plywood and 18 square feet of insulation. Write the constraints on the number of small and large dog houses that he can build with the available supplies and graph the solution set. So the first thing we do is we write the variables. We're going to let x equal the number of small houses, and then let y equal the number of large houses. So then we look for constraints. Whenever we have a situation like this, we always have a given constraint, and that is the fact that x has to be positive and y has to be positive. In the context of the situation, we can't have negative dog houses. But we also can find other constraints, one of which is going to be the fact that he has available only 48 square feet of plywood. So I'm going to scroll down here. There we go. So 48, he only has 48 square feet of plywood. And I'm going to identify another constraint. He has only available 18 square feet of insulation. So that's 18 for the insulation. So what I'm going to do then is write an expression for how much plywood I'm using for the large and small. So reading the problem again, I can see that a small requires 8 square feet. So that's 8x. And then a large requires 16 square feet. So I'm using the 8 and the 16 square feet to get an expression for how much plywood I'm using for each house. With insulation, I can see that the small requires 6 square feet of insulation and that the large requires 3 square feet of insulation. So here are the 4 inequalities that I've got to graph, and I'll do that now. The first 2 pairs, x being positive and y being positive, allows me to actually just limit myself to the first quadrant. So I'm going to do that with this graph. And so for each red and blue, I'm going to produce a table that gives me the x and y intercepts. So let's see. So 0 goes into x, and that would give me 48 divided by 8 is 6. 0 goes into y, and that gives me 48 divided by 8 is 6. So I can tell I messed up. Let's see, if 0 goes into x, it's 48 over 16, which is 3. I'll do the same thing for the red. So doing that for the red, let's see, I've got 0 and 0. So 0 goes into x, and I get, oh, I need a less than sign there. So 0 goes into red, and I'll get 6 for the y-intercept, and 0 goes in for the y, and I get 3 for the x-intercept. So they almost mirror images of one another. So 0, 3, and 6, 0. And then I'll graph the red one, 0, 6, and 3, 0. And just like on the previous example, since both of these are less than, I'm going to be shading beneath the red and the blue, but staying within the first quadrant. So any ordered pair from that shaded region satisfies all the constraints. So this would be the feasible region for this particular word problem. So this would be the solution set of the system of constraints. All right, now we're ready to take this one step further. So look at this problem. This is your first linear programming problem from start to finish. A small doghouse requires 8 square feet of plywood and 6 square feet of insulation. You'll notice that we have the same exact word problem we just did, but they're adding a new component. They're adding, if a small doghouse sells for $15 and a large doghouse sells for $20, then how many doghouses of each type should be built to maximize the revenue? So here's what we're going to do. We're going to pull our feasible region from the last example. All right, so I'm actually just going to make a copy of it over here. So it looks like this. So we had a y-intercept of 3. We had an x-intercept of 6. And pulling in those ordered pairs from the last example looks like this. So this is the feasible region from the example that we just did. That's that feasible region. But what I'm going to do different is I'm going to label the vertices of that feasible region. Now it turns out that where these 2 lines intersect is the ordered pair 2, 2. And you can see from the graph, but you can also tell that when you substitute it back into the constraints, you're going to get the right solutions. So in other words, 8 times 2 plus 16 times 2, that's going to be equal to 48, and it satisfies the other one as well. So 2, 2 is also part of our feasible region. So now that we have the vertices of the feasible region, we're now ready to figure out which one of these maximizes the situation. So the final piece of this is making a table where I note or I log in the vertices of the feasible region. There's 0, 3, 2, 2, 3, 0. And there's actually a 4th one right here on the origin. So there's 4, sometimes they're called corner points, but there's 4 vertices located on this feasible region. The next thing I'll do is I'm going to find the revenue for each of these vertices. So this is the piece where we get $15 per small, and we're going to get $20 per large. So then finding the revenue of each of these looks like this. We're going to take 15 times 0 plus 20 times 3. So if I make 0 small and 3 large, I get $60. And if I make 2 small and 2 large, then I'll get 70. That's 30 plus 40 is 70. let's see, this is going to be 15 times 3 plus 20 times 0. That's going to be $45. And if I don't make any dog houses, I'll get $0. So if we ask ourselves, why did we choose the vertices? It turns out in any linear programming problem, if we want to maximize or minimize a function, it will happen on one of the vertices. It can be any one of the four. You have to check all four. In this case, it turns out that we have two. So two small and two large dog houses will maximize our profit while staying within the constraints of the feasible region. All right, let's do another example. So this is one where we have to minimize. It says one serving of food A contains 2 grams of protein and 6 grams of carbohydrates. One serving of food B contains 4 grams of protein and 3 grams of carbohydrates. A dietitian wants a meal that contains at least 12 grams of protein and at least 18 grams of carbohydrates. If the cost of food A is 9 cents per serving and the cost of food B is 20 cents per serving, then how many servings of each food will minimize the cost and satisfy the constraints? All right, so from the bottom to the top, X is and Y. What are the variables? So X will be the amount of food A. B is going to be the amount of food B. All right, and then we're going to write some constraints. Since we are in the context of amount of food, X and Y have to be positive. All right, we're going to limit ourselves to the first quadrant. And then I see two others over here. I see a dietitian that contains at least 12 grams of protein. So we're going to have a protein constraint, and I see 18 grams of carbohydrates. We're going to have a carbohydrate constraint. So the protein I have to have at least. So I have to have 12 has to be less than how much I'm getting from food A and food B. And so gathering those numbers, 2 grams of food A, and I'm going to add 3 grams, 4 grams from food B. All right, with the carbohydrates, let's see, I have to have at least 18, so that's going to be less than whatever I eat. So let's see, how many carbs? Let's see, 3 carbs, 6 carbs from food A, and 3 carbs from food B. So these are my 2 constraints that I'll put onto the graph. So when we do these, we usually limit ourselves to the first quadrant. So that's why I'm going to just produce a first quadrant graph. And then we usually just find ordered pairs for the intercepts. So for the green one, you're going to see familiar intercepts. When we plug 0 in for X, we'll get 6. 0 in for Y, and we'll get 3. So these are very similar constraints to the doghouse problem. So you're going to see a similar feasible region. So that's going to be the green one. Let's do the blue one. The blue one has X-intercept at 3 and Y-intercept at 6. Okay. The only difference here is look at my greater than or less than sign. Since both of these are greater than, I'll be shading above. So my feasible region is this unbounded region northeast of the boundary lines. So I only have 3 vertices on this one. One vertice. So let's make our table. So I have the vertices I'm going to list out. This is the final step. Let's see. So this one's going to be at 0, 6. Looking at this one. There's one at 2, 2 again. And then there's going to be a third one right there at 6, 0. So then, since these are the vertices, I'm going to plug these into not the profit function or revenue function, but the cost function. All right, so the cost, they're going to tell me here in the final sentence. It says food A costs 9 cents per serving, so that's 9x, and 20 cents per serving, so that's 20y. So I'm going to be plugging these ordered pairs into that cost function, So 0 times 9 plus 20 times 6 is 120. And then let's see, this is going to be 9 times 2 plus 20 times 2. That's going to be 18 plus 40, which is 58. And then 6, 0, it's going to look like this. It'll be 9 times 6 plus 20 times 0. That's equal to 54. So I'm looking for the ordered pair that minimizes cost. My choices being 120, 58, and 54. So my minimal cost will be obtained if I purchase 6 bags of food A and 0 bags of food B. All right, one more example. So from bottom to the top, Sam Dorris manufactures rocking chairs and porches in the Ozarks. Each rocking chair requires 3 hours of work from Sam and 2 hours work from Dorris. Each swing requires 2 hours of work from Sam and 2 hours from Dorris. Sam cannot work more than 48 hours and Dorris cannot work more than 40. So right there, I'll stop reading and write our constraints. So the first thing we do is, what are X and Y? So that's going to be the question, right? So Sam cannot work for more if a rocker sells how many of each item? So X will be the number of chairs, and Y will be the number of swings. All right. Then we have constraints to write out. So I know this. We can't have a negative number of swings and chairs. And then let's look at our description. Sam cannot work more than 48 hours. So Sam has a constraint, and Doris has a constraint. She cannot work more than 40. All right. So let's write the one for Sam. Sam is going to spend 2 hours. Let's see, each rocker, so Sam spends 3 hours on each rocker, and he spends 2 hours on a swing, so 2y. Doris is going to spend 2 hours on each chair, and how much on each rocker? She's going to spend, each swing requires 2 hours, and so she's going to spend 2 hours on each rocker. Okay, so now that we have our constraints, we're going to graph each one onto our feasible region. I'm going to go ahead and place everything into the first quadrant. Let's see, so the red one looks like this. The red one has an x-intercept of 24, and it has a y-intercept of 48 divided by 3, 16. And then I'll go ahead and figure out the blue constraint so that we can figure out our scale. So x, y. So when you plug 0 into each of these, notice that the output for the other one is 20. So I made my axis a little bit bigger here. I think I can go by 2s on this. So let's see here. 2, 4, 6, 8, 10. 2, 4, 6, 8, 20. And then 2, 4, 6, 8, 10. 2, 4, 6, 8, 20. So let's see. The red one will have intercepts at 24 and 16. And the blue one will have intercepts at 20 and 20. Okay, and we note that each of these are shaded less than, so we got to shade less than these, and we're going to have a feasible region that looks similar to the dog problem. It's a quadrilateral and it's stuck in the corner of the first quadrant. So I can identify the intercepts for the feasible region. This one was at 0, 20. That's that corner point. This corner point was the x-intercept of the red line, which is 16, 0. But what about this one? We can guess it's going to be around 6, 16. What we might have to do is go ahead and solve the system to do that. So I'll go over here and do it. So I'm trying to find the intersection point of these two lines. And it's not horrible if we go ahead and solve the system to get the answer. This is easily done with elimination. So I'll just multiply this equation by -1. I'll get -x is the same thing as -8. So that means that x is equal to 8. Well, if x is equal to 8, then that means that 16 plus 2y is equal to 40. And so y has to be 12. So that corner point is 8, 12. So with these 3 corner points, and actually a fourth one, we're going to go ahead and calculate what is the profit for each one. All right, so let's make our table where we write down the vertices. The vertices being 0, 0, 0, 20, 8, 12, and 16, 0. So one of these 4 is going to maximize our profit. Rocker cells. So there it is. For rocker cells for 160 and the swing cells for 100, what is going to be the maximum profit? So that's going to be 160x. So the profit is 160x plus 100y. I'm going to go ahead and calculate how much I'll make if I produce this amount. So that'll be 0. If I make 0 rockers and 20 swings, that's going to be $2,000. If I make 8 rockers, let's see, 8 times 160 plus 100 times 12 is 2,480. And then the final vertex is going to be 16 times 160 is $2,560. So the pairing that maximizes revenue is going to be the 16-0. So if I want to get the most money and stay within my constraints, I'll make 16 rockers and 0 swings.